All right, so next we're going to talk about using DeepHyper for uncertainty quantification. And thanks to Rama, who gave me his slides on this topic, and I was able to adapt them for today. So there's a lot of reasons you might want to have uncertainty quantification with your machine learning model. You want to be able to know how confident this machine learning model is for a particular input. And this could be because you want to build trust, especially if you're sharing your model with someone else and it's safety critical. But it could also be used to improve your model, such as you want to do active learning to gather more training data where the model is uncertain. And there are two main sources of uncertainty. One is called aleatoric uncertainty, which is a property of the data. So for example, the data is noisy and there's kind of nothing we can do about that, but we can quantify it. And the other is epistemic uncertainty, which people call knowledge or model uncertainty. And we can reduce epistemic uncertainty by collecting more data, improving the model, and so forth. And I'll demonstrate these two ideas with a plot. So here we have some gaps in the training. The training data are these blue dots, and there are big gaps where we don't have any data. And so in those gaps, that would be a lot of epistemic uncertainty because the model just really doesn't know what it should be doing in those gaps. And that could be alleviated by collecting more data. But we can also see on the left side, the training data is more spread out. It's more noisy around the real linear function. So that's high aleatoric uncertainty. And on the right side, there's less noise. It's more closely matching the real linear function. So that's low aleatoric uncertainty. And I'll keep repeating what aleatoric and epistemic mean when they come up later, because I think those are hard words to remember. Here's another example. So you have an input image on the left, and you want to do a segmentation. So the second image is the ground truth of how you would segment this image. And the third image is one segmentation. Now the aleatoric uncertainty is when the data, we've got like some noise from the data, and it makes sense that it's like along edges of the segmentation. And here we have some epistemic uncertainty, and that's more like where the model is wrong, or this particular, we can see in that semantic segmentation, we can see where it's confused, and that kind of corresponds to the epistemic uncertainty. So we have a paper called AutoDEUQ that was accepted at ICPR, and this is one approach to quantifying uncertainty. And we're talking about it today because this method is now built into DeepHyper. And the first author here is Rama. The big picture idea is that you build an ensemble of diverse neural networks, and then you use them to sort of vote on what the prediction is. And this helps you quantify uncertainty. So if you have this ensemble of neural networks, and it's a hand-wavy explanation, if they're all agreeing, then you're more confident in your prediction. And if their predictions are more spread out, then you're less confident. That's kind of the hand-wavy explanation. We use the training and validation data for a joint hyperparameter and neural architecture search, and that gives you a bunch of trained neural networks, which we're calling a catalog here. And then we have way to select an ensemble from as a subset of that catalog. And I'll talk more about that. So a little bit more about the joint neural architecture and hyperparameter search. For the neural architecture search, it's an aging evolution algorithm. And for the hyperparameters, it's a Bayesian optimization. Sorry, I might have said that wrong. Okay, so we're jointly doing this aging evolution and Bayesian optimization. The aging evolution is like a genetic algorithm where you have like a good candidate so far, and then you do some mutation to create neural architectures for the next generation. And you continue your search. Then we have the step of you've done this joint neural architecture search and hyperparameter search, and you have a bunch of models, but we're not going to use all of them for the uncertainty quantification. We want to take a subset to be our ensemble, and we use a greedy heuristic. So here on the left is the catalog of possible models that have already been trained, and we want to create an ensemble. And the greedy heuristic is that at each step, we add in the neural network that best improves the loss of the ensemble so far. So we iteratively add more. And it's greedy, so it's not necessarily a global optimum, but it's a reasonable heuristic. Now, to estimate the uncertainty, remember we had those two kinds of uncertainty. There's the aleatoric and the epistemic. We have each neural network estimating the aleatoric uncertainty by having the loss function of the negative log likelihood. And that means that the neural network is outputting a mean and standard deviation for each prediction. Now, but we also wanted to capture epistemic uncertainty, and that is estimated through our ensemble of neural networks. And to make that a little more mathematical, we want to, given an input to a network X, we want the probability of the label or output Y. And we're able to prove in the paper that the variance can be decomposed in this way, where we've got this term for the aleatoric uncertainty, and we have the term for the epistemic uncertainty. And the formulas are in the paper for how you can estimate the mean and variance from your ensemble of models. Just a quick overview of what's been done before. So ideally, you have a fully Bayesian neural network where each parameter can be sampled from like a complicated distribution, but this is computationally difficult. And so there are different approximations. For example, Monte Carlo dropout, where after training, you still do dropout, you randomly remove nodes. And this, you do this many times, and this gives you like an ensemble of predictions. And you can also do like a variational inference approach. And there's also a whole set of papers in the literature about deep ensembles. So similar to what we're doing, you have an ensemble of neural networks. And part of our contribution is having these ensembles be very diverse because we did this wide neural architecture and hyperparameter search. So I'm going to show some results in comparison against some of those previous papers. Here's a toy data set where the real function is this oscillation, but the training and validation data are just in these certain regions. And so you can see here, we have more aleatoric uncertainty on the right side than the left because that data is more noisy. And then also we have these gaps with no training and validation data. So that would be a lot of epistemic uncertainty. And so we want to see how well our method can capture the aleatoric and epistemic uncertainty. So here are some results on this data set. On the top left is our full approach. And so we see in gray the real function. And those gray bars are the regions where we have training data. And so the model is doing nice predictions in those gray regions. And we see, as expected, that the uncertainty is wider in that right region where the data is noisier. So that's that aleatoric uncertainty. And then we also expect to have a lot of uncertainty between the regions of training data. And we want that uncertainty range to contain the real data. So ideally, it's well calibrated, that you're not too narrow, that you're not including the real training data, and you're not too wide, that you're just like very overly unconfident. And in this slide, it's a ablation study. So looking at how important the different pieces of our algorithm are. In plot B, it's just the neural architecture search with aging evolution. In plot C, it's just the hyperparameter search with the Bayesian optimization. And in plot D, the neural networks are initialized with random weights. And then we also looked at a set of regression benchmarks that have been used in these prior papers about uncertainty quantification. So it's all regression, not classification. And there, you can see there's a little bit of variability in their sizes. And to kind of condense down these comparisons, you can see the full details in the paper. We have these bar charts. On the left is the negative log likelihood, which is trying to incorporate both the error and how well calibrated the uncertainty is. And on the right, we have just the error. And we ranked how well these different methods do on these data sets. And so here we're comparing, we rank how well the methods do on each data set, and then we average the rank for the method. So here we have each method, and the lowest one is AutoDEUQ, our method. So on average, it's ranked something like 1.5. So it's typically the best method, or at least close to the best method. And you can see the full details in the paper. But to summarize, the goal is to quantify uncertainties. And there are various ways to do that for neural networks, but deep ensembles are very competitive. And specifically, we have this method called AutoDEUQ. And we beat state of the art on many of the benchmark data sets that are used in previous papers. And we're able to prove this law of total variance that has a decomposition between the aleatoric and epistemic uncertainty. And one nice thing is this is built into DeepHyper, so we can try it out today. And I think one nice thing about this way to do uncertainty quantification is if you were going to do a neural architecture search and or a hyperparameter search anyway, maybe you're interested in that because that's why you're at this workshop today, then you can kind of get uncertainty quantification for free. And stronger statement, using your ensembles to make like a vote to make your predictions, even if you don't care about the uncertainty quantification, gets you better errors than just using your top model. And we're going to see that in the notebook. So it's kind of like a democracy. Instead of just relying on one neural network, have everyone vote, you get better results. Any questions before we go into the hands-on? Okay. Christian, let's can take it away with the hands-on, and feel free to add any comments.
Thanks, Bethany. I think there was a question, interesting question on dropout. So, how do we get the uncertainty using dropout or not? So probably that will be sort of clarified here in the hands-on, where we will be using a mean and standard deviation in the output layer, or mean and variance in the output layer, and use negative log likelihood as opposed to mean square, a mean squared error as a loss function. So so dropout is another way to do that. But what we have observed in our benchmark study, also the one that Bethany presented, dropout UQ are not as good as ensemble uncertainty. So in the uncertainty quantification literature, there are two different classes of methods. One is Bayesian neural networks. The other one is ensemble, and ensembles are sort of the gold standard for many uncertainty quantification tasks, where the idea is to build multiple models. Or previously, it's all about like, okay, start with same architecture, same hyperparameter, change the random seed, and then build different models. And as we found out that you can get uncertainty in that way, but it's not as robust as ensemble, where you have diverse set of models, right? So and the same problem with the dropout as well. So with the dropout, we didn't see good uncertainty as we could actually get with an ensemble. And also the other nice thing about ensembles is the decomposition of the variance, where we can tease out the aleatoric from epistemic, which is a very very important thing in many different tasks. For example, if even if you have uncertainty, do you want to see like whether this uncertainty is coming because of the model or because of the data? If it is because of the data, you have to go and improve the sensor resolution, for example, right? If it is coming from the model, then you can use that to adaptively select points or do active learning, or select, do lot more data, targeted data acquisition. And many of the methods, including Bayesian neural networks, do not provide that decomposed uncertainty, which is a nice advantage of ensembles in general. But in particular here, we are trying to do this in a much more automated way.